Good afternoon, professors. We are Group 45 and in this video, we will be presenting on our machine learning project. The Kaggle competition that we have chosen is Costa Rican household poverty level prediction. Here is the agenda for the presentation. Firstly, I will explain the problem statement and challenges faced. Next, we will cover the proposed solution and conclude the presentation. Now, let's begin by understanding the problem. Many social programs face difficulty in ensuring enough aid is given to the right people, as typically, the poorest segments of the population are not able to provide their income and expenses records to prove that they qualify for aid. As such, proxy means test, PMT, is one of the popular methods to verify income qualification by allowing agencies to use a model that considers the family's observable household attributes. Although using PMT is an improvement, as the region's population grows and poverty declines, accuracy remains an issue. Therefore, the aim of this project is to predict the poverty level accurately given the dataset of Costa Rican household characteristics. Next, the first challenge faced is imbalanced class problem. With fewer examples for extreme, moderately and vulnerable classes, the machine learning models can struggle to predict these minority classes. Another challenge is the need to aggregate individual household members' data to the household level, as the scoring of the competition is based only on the predictions for head of household. Moving on, we will look at the proposed solution, which consists of these 4 steps: data cleaning, feature engineering, modeling and experiments. In the first step, we start by exploring and cleaning the dataset. Here is a summary of what we have done: correcting wrong label and outlier, filling in missing value and imputation. Firstly, we have found that some labels are incorrect, as there are 85 households that do not have a unique target value for each family members. Based on the competition discussions, the organizers mentioned that the correct label is the head of household. Thus, we have corrected the labels for households with members having different poverty levels by assigning the true label for all members. Next, we found an outlier in res ESC column. Based on the competition discussions, the maximum value for this variable is 5. Thus, we have set all values greater than 5 to 5. Next, we found that V18Q1, the number of tablet owned by a family, contain missing values. Our hypothesis is that those with null values simply do not own a tablet. To prove our hypothesis, we compared with the Boolean variable, V18Q, which shows whether a family own a tablet or not. We found that those with null value for V18Q1 also have value 0 for V18Q. Thus, our hypothesis is true and we have filled in the missing values with 0. Another variable with missing value is V2A1, which shows the monthly rent payment. Our hypothesis is that household with missing value own their home and do not have to pay any rent. To investigate this, we plotted this bar chart to show the distribution of home ownership status where household rent payment is missing. We can observe our hypothesis is true, as majority of them generally own their own home. Thus we set V2A1 to 0 if they own and paid off their home. For other home ownership status, they will be imputed in a later step. The last column with missing value is res ESC, which shows the years behind in school. Our hypothesis is that families with null value do not have any children in school. We tested this out by finding the ages of those who have a missing value in this column, and the ages of those who do not have a missing value, and found that the oldest age with a missing value is 17. Based on the competition discussions, we discover that this variable is only specified for people aged 7 to 19. Anyone younger or older than this age range is likely to be no years behind, so we have set it to 0. For missing value outside of the range, we will impute it later. At the final step to deal with missing values, we have imputed the remaining missing value using the column's median value. We chose median as it best reflects central tendency, which works well for continuous data and is not influenced by outliers. After data cleaning, we performed feature engineering to transform existing data into more meaningful input data that is compatible with the selected models. In this project, our team performed 3 levels of feature engineering: general level, household level, and individual level. Here is a summary of what we did in the general level. Firstly, to aid in feature engineering operations later, we have categorized the variables into 4 categories and further differentiate them according to their data types. Next, we notice that squared variables is not applicable for our proposed solution, as it is more useful for linear model. Moreover, the correlation matrix shows that the squared variables such as SQ Bescalari, SQ Baget are highly correlated with their original unsquared variables. Therefore, we have dropped them to reduce feature dimensions. After making some reduction in feature dimensions and exploration, we have concluded the top 5 most positively and negatively correlated variables as shown. We noticed that the positively correlated features tend to describe the education situation in the household. Next, we plotted the years of education of household head against poverty level and found that household with a lesser year of schooling tends to be poorer, and the years of education for male head have a higher positive correlation with target than female head. Moving on to feature engineering at the household level. Firstly, we subsetted the dataset based on the head of the household and created a new data frame to hold all the household variables. Secondly, we removed highly correlated variables and kept most of the household variables to use as the features. Thirdly, we constructed new features in household size using subtraction and ratio, per capita and combination of relevant features per household. We derived new features for household level by using simple calculation, subtraction and ratio, to denote the household population information based on the household size. Higher child and elderly ratio in a household will definitely lead to higher dependency rate and more financial stress on the head of household. Here are more new feature for household level. We also derived new features based on some essential factors such as housing and electronic gadgets that potentially represent the poverty level of a household. We decided to use per capita instead of actual numbers, as it helps to remove biases due to different household size. Lastly, we grouped relevant features together, as it is efficient to understand what factor contributes to the poverty level of a household. After feature engineering at the household level, there are 396 features in total. For feature engineering at the individual level, we similarly subsetted the individual variables by adding the individual variables in arrays we defined previously. Next, we dropped individual variables such as male as it is highly correlated to female column. Next, we encoded the 9 education level which are originally one hot encoding into an ordinal column. Lastly, we constructed 3 new features using ratio of age and grouped relevant features into a single feature using summation. Next, to incorporate the individual data to household level, we have aggregated each individual variable by grouping using their household ID and used various aggregation functions including min, max, sum, count, standard deviation and range on each individual variables. Finally, we dropped all highly correlated columns with correlated value greater than 0.95 and merged the remaining features with the household level features. After feature engineering, the final feature set has 491 features. Moving on to the modeling step, we tried to create baseline models by experimenting and fitting various algorithms that are suitable for supervised multi-class classification problems. The 5 model we used a decision tree, Gaussian, k-nearest neighbor, random forest and gradient boosting. Firstly, for decision tree, we first fitted a tree using all available features but found that by limiting the input features to Nejc and Cielarazo, the top 2 highly correlated features to the target, we are able to obtain a higher accuracy. We also set max_depth equals 3 to prevent overfitting. Secondly, for naive Bayes, we choose Gaussian algorithm instead of other algorithm as Gaussian is most suitable for our project, by looking at the distribution count of the selected features and determines where the cutoff point to classify the household into the 4 different poverty levels. Thirdly, for KNN, we have tried various values of k and choose k equals 12 as it has the highest accuracy. Fourthly, random forest is a more advanced model that combines multiple decision trees to get a more accurate and stable prediction. We set the n estimators to 100 which is the number of the trees we want to build before taking the highest voting. Although a higher n estimator leads to better performance but it is constrained by the limitation in time, memory and processor. We have no restriction in the number of processes allowed to use by setting the n jobs equals -1 as we do not want to waste resources by over-allocating processes to the task. Random state is set to 10 to ensure that the output of each run will be the same. Next, gradient boosting is also a technique that combines decision trees like the random forest, but the combination process starts at the beginning instead of the end. Hence, gradient boosting produces a prediction model in the form of an ensemble of weak prediction models. XGBoost, extreme gradient boosting, has been the de facto choice in many data science competitions simply because it is extremely powerful. However, light gradient boosting machine, LGBM, improves on XGBoost as it outperformed in training speed while attaining comparable performance. Therefore, we decided to use only LGBM under the gradient boosting type. For the LGBM parameters, to deal with imbalance class problems, we have set the class weight to balanced so that it assigns the class weight inversely proportional to their frequencies. We used 400 early stopping rounds to stop training once the validation score does not improve, and 0.93 column sample to randomly select a 93% subset of features for each iteration which helps to prevent overfitting and reduce training time. To achieve better accuracy, we have decreased learning rate to 0.03. Finally, to compare the performance of these models, we used the 5-fold stratified cross-validation. We chose stratified cross-validation as it helps keep the same proportion of different classes in each fold which is useful to counter imbalanced data problems. we have set the cross-validation scorer to be macro F1 score, the same used by the project organizer. Based on the baseline performance as seen from the bar chart, we decided to rule out decision tree and Naive's Bayes and proceeded to experiment with KNN, random forest and LGBM to tune the parameters and further improve their performance. After the modeling step, we move on to experiment, which consists of feature importance, feature selection and ensemble of different algorithm. Based on the trained LGBM model, we produced this bar chart to visualize the feature importance. Similarly for random forest, the bar chart shows the feature importance. By comparing the both feature importance ranking, we observed slight differences in the features selected, while some features with high importance in both models include mean-egic, age-min, escalari and age-sum. Moving on to feature selection, due to the huge number of features after the feature engineering process, we have decided to experiment with feature selection to select a subset of features that contribute most to the prediction and to discover the relationship between the number of features used and the accuracy of our model. We used recursive feature elimination, RFE, to fit a model and recursively removes the weakest feature until the specified number of features is reached. RFE also attempts to eliminate dependencies and collinearity that may exist in the model. We have decided to include cross-validation with feature selection to mitigate overfitting. The chart shows the results of performing RFE-CV on random forest and LGBM models used in the modeling step. For random forest, the macro F1 score peaked when using the top 59 features with an oscillating trend afterwards and generally decreased slightly as more features were used. For LGBM, the macro F1 score peaked when using the top 13 features and decreased dramatically as more features are used. Therefore, in our experiment, we retrained the random forest model using the top 59 features and denoted the result as RF_cell. We also retrained the LGBM using the top 13 features and top 59 features. From this experiment, we observed that the score for random forest with feature selection improved significantly, whereas the score for LGBM with feature selection score remained comparable as before. Furthermore, in an attempt to improve accuracy, we further experimented with ensembling different algorithms. We decided to use a voting ensemble, which is an ensemble machine learning model that combines the predictions from multiple other models to achieve better results. We decided to ensemble the KNN, RF and LGBM models as they have the higher score previously. We also observed that their predictions are merely moderately positively correlated, which indicate they are suitable candidates to be ensembled. To produce the prediction, we have used soft voting, which involves summing the predicted probabilities for each class label and use the class label with the largest probability as the prediction. The two ensemble classifier are ECLF, which ensemble KNN, RF, LGBM with the whole feature set, and ECLF_cell, which ensemble KNN, RF and LGBM using the top 59 features. Next we replot the bar chart to compare the models. We observe that the score of the ECLF did poorer with higher standard deviation, while ECLF_cell attained a comparable score with RF_cell but is still worse off than using LGBM alone. Finally, the final model used for the competition is LGBM_RF_cell, which has the highest macro F1 mean score and lowest standard deviation. In conclusion, throughout this project, we learned that the crucial step in having good model performance is feature engineering. By constructing the features, we can explore those variables highly positively correlated to the target and filter out the redundant variables to reduce the dimension. The input feature to the model will determine the performance of the models. Next, in some models we used in the project, we could have better performance by testing different values for parameters used in the models. For example, in the random forest modeling, the F1 score could be better if we increase the n_estimators, number of trees to build, to a higher value. However, it is often trade-off by the memory and time consumption. Lastly, we also learned that running complex model algorithms on a large dataset required a sufficient amount of CPU memory, as it takes up a lot of resources and time running in the Kaggle platform. In the end of the project, we have made several submissions to Kaggle and obtained best score of 0.44334 for both public and private score, and ranked 22 out of 616 in public ranking and 21 out of 616 in private ranking. Here comes to the end of our project presentation. Thank you for watching.